I have Dr. Leonardo Barilaro from MCAST. Now, I know Dr. Barilaro 15 years, as I was saying. We worked on Rexus Bexus. I don't know if you're familiar with that. It's a sounding rocket and high altitude balloon student experiment. Some people here might be interested in it. So we have some interesting content here, but we also have opportunities like that you might find your research after you finish your PhD or during your PhD. You could develop, we're interested in experimental payloads, and we recently been working on an adaptation of TIBA's research for cold welding, and that is for a project called Astrobeat, which Leo will explain further. And that's launching on to the ISS in October. And we're kind of working on that in parallel with our research. That's, I mean, there's always opportunities if you need qualification. Say, I know your nozzle deposit and thermal deposits in space, for example, might be a nice project. The Astrobeat is developing into a new project called Saboreg or Spartacus, which has got to do with 3D printable repair patches for primarily aircraft. So if anyone's in the area of 3D printing, might also be of interest for you. Dr. Barilaro goes by another pseudonym, which is the Space Pianist. So if anyone's any interest in composition, he's probably the world's renowned and the only unique space pianist. Combination of music and science. I think it was last year, the year before, he had some compositions broadcast from the space station, which was, I think, one of the first. But I'll let Leo explain what I probably did a poor job at himself, and you can carry on with the presentation. Thanks.
Thank you very much, Mark. A very nice introduction. So I have less things to say about myself. Happy to be here. I'm here today within the framework of a so-called SPARTACUS project, that is a project that I'm following at MCAST, the institution that I represent, the Malta College for Arts, Science and Technology. And is a project that is a follow-up, a building up on two big projects. One is Borek, one is Astrobeat, and I will go more in detail. But before going more in detail, okay, brief introduction was already made by Mark. I am an aerospace engineer, senior lecturer in aerospace engineering in Malta, and I also do research and teach about aviation. And I'm also a musician, space pianist. Why? Because I'm sending my music to space, and there is also something beyond just the fact of it's a very cool stuff to do, sending music to space. And at the end, I will spend a couple of minutes to explain what is behind this project. So before going in detail about the two big projects that are the foundation for Spartacus, I will provide you a quick overview about space debris. I'm sure you know what they are, but I will go a bit more on the technical side, also to provide you some inputs and maybe to spark some curiosity and interest and for potential research in the future. So, you know, you have to imagine our orbit, above all the low Earth orbit, as a very crowded orbit. And it's true that in space there is a lot of space, but the most commercial orbits are heavily populated by what we can call space junk. So imagine these small pieces of metal, because it's 99% aluminum still nowadays, that are traveling crazy fast at very high speeds and can impact space structures with a very high probability. Now, I will not go too much in detail about it, but here you see some famous examples of damages, for example, in the cupola of the International Space Station, on the Canadian Arm, on the solar array of a Sentinel satellite. And these impacts can have a different level of criticality. They can be a problem or they can be a catastrophic failure. Now, if a space debris goes too fast and is too big, against a catastrophic failure, there is nothing we can do. If the ratio between the mass of the debris and the mass of the impacted spacecraft is too high, we can't really protect. The gray area where the research work focus is about smaller impacts. So now, about space debris. The focus is mainly on the man-made objects, so what we call space debris. There are also the micrometeoroids that are a threat, but what is more concerning for the commercial aerospace industry are the man-made objects. And when there is an impact, we call it a hypervelocity impact because the speed of the debris that is impacting a spacecraft is higher than the speed of sound in the propagating material. So if we are talking about aluminum, is over 4 kilometers per second. So I'm sure you know the equation of kinetic energy that goes with the square of the velocity. You can easily imagine the amount of energy that these impacts have and in conditions that we don't have here on Earth. So we are talking about millions, hundreds of millions of objects where there are thousands of very big objects. Now, big objects are trackable from Earth, and as it happened many times also for the ISS, you can do avoidance maneuvers. So you can avoid, luckily till now, they always manage. For intermediate objects, is a critical area because you can, some cases, track them, and also tracking techniques are improving. But what you can do is only passive shieldings. But the biggest threat comes from objects that are between 1 millimeter and 1 centimeter of diameter in size. That is the area where the studies for passive shieldings, sensors, and so on is more focusing on, and where there can be an active improvement of the technology that we have. And I started dealing with space debris in Padova, that was 2008. So now I saw the evolution of the industry and research on the subject now for quite a while. So from where they can come? They can come from explosions, like when there was the Chinese satellite test where Chinese wanted to prove, above all to the Americans, that they were able to take down a satellite. So they did with one of their own satellites. Problem is that it was a very big satellite that in 2008 spiked the population of space debris, creating a lot of problems. Can be small flakes of paint, of MLI, propellant exhaust, failures, and above all, they can come from other impacts. Now, there is a syndrome that, a scenario that you probably heard of. It is called the Kessler syndrome. Kessler is the scientist that already in 1978 predicted this. So we are risking that the increase of impacts in orbit will lead to a sort of domino effect where the access to orbit will be no more safe. Already like 10 years ago, these levels, the levels that were set by NASA, were very close to the limit to send safely an astronaut to orbit. What did they do? They changed the limit because still the problem is only increasing at the moment, even though mitigation techniques are improving. So to give you an idea of the energy involved, because for our daily experience is not so comfortable to imagine it. Imagine this small sphere is 1.5 grams, so it's very small. L'aluminium sphere traveling at 10 kilometers per second has more or less the energy of a crash test done with a medium class car or a hand grenade exploding. So imagine you have your 3 units CubeSat, which is literally 30 centimeters by 10, that is in low Earth orbit, that gets an impact, basically a car crashing onto it. If you put this on a terrestrial image, gives you the idea of the energy involved and of the level of protection involved. Now, just to mention quickly some effects, besides the damage, so from the obvious, you have a manned module, you have astronauts inside, there is a hole, astronauts inside are not happy, of course, to put it in very simple terms. But there are more subtle problems created by space debris impacts. For example, the loss of spacecraft attitude, because you transfer momentum, that creates a problem. Imagine for instruments that are pointing Earth or pointing other celestial bodies, that is a problem. Deterioration of optics, so scientific instruments where it's not easy to go there and change the optics. Thermal control surfaces, solar panels, so the production of energy and so on. So these are just very small examples. Plus, of course, you can have damages to what is inside after the shield. So one point is to estimate the level of damage, because now things are improving, but before there was only the pass or no pass criteria. This is what we were able to study here on ground on Earth. But the problem is, yes, a debris perforated the spacecraft hull. But how big is the damage? How much I'm damaging the electronic that is behind? And just to mention another important concept that I hope the videos now will work. You see, when there is an impact, there is the creation of what is called ejecta debris cloud. Those are smaller debris that are also them an issue. Here we have another test where you see this debris cloud that goes on what can be an electronic, a PCB, an instrumentation. So you want to know also how much bad, to put it in simple terms, is the impact for your instruments. So after this very quick overview, just to pinpoint the main concepts on which I'm working in collaboration also with Mark now since some years, I introduce you what I'm doing in Malta as a researcher. So Malta from this year joined the ESA plan for European cooperating states, which means bigger opportunities for research funds and the opportunity to take part in bigger projects. There is a governmental entity called Scienza Malta, which is basically a governmental body that creates competitive grants where you submit your proposed research, and they give some funds, till now still very small, unfortunately. And I'm working at MCAST, which is the Malta College for Science and Technology, Art, Science, and Technology, that started just less than 4 years ago, the aerospace program. So the focus of this presentation is on the 2 main projects that Mark mentioned. One is SPARTACUS that just ended last month, and one is Astrobit, still ongoing. SPARTACUS focused on the smart design in the developing a methodology to design shields, 3D printed shields with materials like carbon fiber and Kevlar for both aviation applications and space applications. For aviation applications, the focus is mainly for MRO, so for maintenance and to speed up the process, the current processes that there are when you have to deal with repairing of damages, above all from high energy impacts. And for space applications, imagine you can 3D print with the shapes that you want, and you can optimize weight and area to mass ratio for space applications, so imaging small satellites. The other project is Astrobit, where basically we developed a small 1 unit, so 10 by 10 by 10 test rig to test a concept that is called welding adhesion, and I will go more in detail soon about it. So, about Zborek, as I was saying, the focus has been double, both for aviation and for aerospace. And here there are some examples. So, one was the focus was on developing a procedure for aviation, which is, imagine an aircraft. A typical example of a high energy impact can be hail strike, can be bird strike, nowadays also drone strikes that can happen. And you have damages that depends where you are in the world and how good is your facility. So, and also the availability of the material you have to repair. So, one solution is to do a temporary repairing. So you do put a temporary patch and for a while the aircraft can still fly. The other solution that is the more desirable is the permanent repairing. So nowadays these patches are done in a traditional way. So it's a multi-layer, can be carbon fiber, epoxy resin and so on, and they are placed. They can be sized accordingly. But here the concept is, what if a MRO facility has its own 3D printer? There is an aviation qualified procedure. You 3D print the patch that you need to repair your damage, because the damage can be on the undercarriage, can be on the rudder, can be on the leading edge of the wing. So you can have different type of damages. And the other point was, let's see if 3D printed shields with using carbon fiber and Kevlar are behaving at least good enough as traditional shields, which are Whipple shields, which are multi-layer shields, and single shields. Here, just for your reference, you can see two examples of high energy impacts. That was a bird strike. You can still, unfortunately, still see the blood and pieces left by the bird, but this is something that happens very often in aviation, and very often there are repairings that needs to be done quickly. Imagine here in Dublin, you have the headquarters of Ryanair, the numbers of spacecraft, soon maybe, of aircraft that flies, and how demanding is the schedule for who is managing MRO. So they are really tight schedules. So here you see on the left and on the right side patches that have been tested for aviation purposes. And here you see, so from outside you don't see the secret sauce, but these are single plates printed in with different philosophies, and multi-plate. Here you can see these are two multi-plates printed in a different way, but as aesthetic are the same. And then here you see another one where we tested this wave-shaped layer plus two thinner front shield layers to check with the simulations the tests that were done, experimental tests that were done in the lab. Another thing that I will quickly mention is one of the strong points of Zborek is that usually to simulate, so I don't know if here there is someone that is into structural simulations, but you can't simulate high energy or hypervelocity impacts with traditional ANSYS, with a workbench or equivalent. You need a different technique that is called SPH, which is smooth particle hydrodynamic code, where basically a solid shield is modeled with very small spheres, very small balls that has, from a mathematical point of view, a total different management in comparison with traditional simulations. Now, these simulations are super hard to set up still nowadays. They need a lot of tests to be validated. And above all, for more exotic materials, they're still unreliable because it takes a lot to properly characterize the equations that work for these SPH codes. And they are very time consuming. So if you have a normal laptop, a simulation can last days, a basic one. If you arrive at the end, you discover that it's wrong. So this can be a problem above all if you are in a research institute where there are master students, PhD students, and the resources are not so big. So since also in Malta we are still young and the research group is still small, I wanted to develop in collaboration with SkyUp Academy in Italy a new technique. Now, SkyUp Academy is basically a VFX academy. So they teach at a very high level students how to do the special effects that you see in Hollywood and in video games. Now, how we found emerge? Because when you see the explosions in Hollywood movies, they used a particular type of softwares. This softwares uses a totally different approach, GPU-based, to simulate the physics of, I don't know, there is a rocket that is sent to make an asteroid to explode. And they look very realistic because our eyes are tricked. So I think, if they are realistic enough, can we find a point where these amazing effects are supported by actual physics? And we made it, at least the first steps. We are not the first in the world, but still there are very, very few people to do it. So it's a field where there is something to do. So basically, the simulation that now you will see is done using Hollywood resources, which means this simulation took 8 times less than a traditional SPH simulation, and this was done in 3D. Now, the tricky part, of course, is that you need to validate with experimental tests, and this is what we are working on. But from a point of view of doing a preliminary research, printing a lot of shields and wanting to have an idea of where you are going, even though it's less accurate of an SPH simulation, is much faster and you can do many more. If you do a mistake, maybe you lose 1 hour of running time on your laptop and you are not too sad at the end of the day. If you do an SPH simulation after 1 week, you see that makes no sense, you become much more sad for the weekend. So this was a very academic approach used. So now let's go to the real test. So here you see a simple plate printed with carbon fiber and Kevlar. So we are using a dual nozzle 3D printer. And here you see the photograms of one of the first tests, where you can see what I mentioned, the ejecta cloud. So you want to limit the amount of debris, and also you want them at lower speeds, of course. And this is influenced by the design. And here, in the next slide, which is one test done on one of the Zborek shields, where you can see the propagation of the debris. This was a test done at 3 kilometers per second with a 3 millimeters sphere. This thickness is 10 millimeters of a 150 by 150 shield. So this is the effect of, if you have a caliper, a ruler, you can get an idea of how much is 3 millimeters. At 3 kilometers per second, this is the level of destruction. So imagine the debris cloud is around 1 kilometer per second, let's say, roughly, hitting on your electronic, on your PCB. Nowadays, there is above all for smaller projects, is a consumer electronic that is sent to space. So that is a significant amount of damage. Now, this is most of the team of the smaller project. This was a photo taken at the end of the project, where there are the people that worked on in Malta on the project. On the left there is the not the president, the CEO of SkyUp Academy, and on the right there is near me the director of the Aviation Institute. Now, going to the next project, Astrobit. So you saw now how I'm leading research about 3D print shields. Now we go to Astrobit. Astrobit was born thanks to the collaboration with Dr. Wylie. Exactly 3 years ago, the August of 3 years ago, we were talking about common research that we were doing, and we put together our know-how to develop what now eventually became Astrobit. So it started now a while ago. So here the main concept is to use cold welding to repair damages created by a space debris impacting a spacecraft hull and doing a hole. Now, usually, I put this photo to remember that it's Dr. Wylie. And now here we were at a conference in Padova, where was also presented a previous step of the research about Astrobit. So basically, here the main concept is you have 2 metal surfaces. Historically speaking, cold welding adhesion, where you have the adhesion of these 2 metals, so you have a literal welding, because you don't have the effect of the atmosphere, plus you have microgravity conditions, was seen as the devil in the space environment. Why? Because you don't want to have accidentally components that get stuck. An historical example, even though it's still debated, was a Gemini 4 mission, where there was the first EVA, first space work. And when the astronaut was going back into the Gemini capsule, the hatch got stuck. So it was not possible to close the capsule. So imagine you are up there, you get a bit upset, most likely. With some brute force, they managed to close the hatch to re-enter safely on Earth. Another historical example is the Galileo mission in the 70s, early 70s, where a mission to Jupiter, where the mission had a big antenna that was required for deep space communications, so to send the data back to Earth of the what was being analyzed around Jupiter. But the point is that it was a big antenna, so they designed it as a sort of umbrella, so you can conveniently pack it in a rocket, send the rocket, and the idea was that when you were close to Jupiter, you were opening your antenna and starting communicating with Earth. What happened? $1 million mission. They didn't have the knowledge to consider the cold welding effect. So basically, when they started opening this umbrella to have the full deployed antenna, it got stuck because in the meanwhile, the cold welding happened. So it's something that definitely you don't want in space. But since me and Mark, we like to think out of the box, we are trying something different. We thought, why we don't use this to our own advantage? So you have a hole, you have an impact. We want to close that hole with the concept of a portable test rig, and you can do something quickly, because nowadays there is still no standardized procedure, and there are techniques that are being investigated, but there isn't so much. So just to give you an idea, here is a photo from the first EVA, extravehicular activity in 1965, Gemini 4 mission. Some examples of cold welding between 2 pieces of aluminum, which is down on ground. And something that I saw on an episode of Black Mirror, in case some of you was watching the series, where you have the actor that did Jesse Pinkman in Breaking Bad, that I forgot his name now, that was the actor taking part also in this episode. And at the beginning of this episode, there is he's in space, there is an emergency, and he goes and he does welding, traditional welding, to fix a damaged component in the spacecraft in which he is. So here the idea is to pass from science fiction to science, doing welding, but of course not the traditional one with TAG that probably was doing the movie. So just to give you an idea, now, thanks to SpaceX, costs has been cut down of a factor of 10 in the last year, but sending stuff to space is still very expensive. So, I managed to secure the funds in Malta, but still the amount of funds is barely enough to send a 1-unit experiment on board the International Space Station. So in total, we have a mass budget of 1 kilo, with a detail that the interface plus the aluminium cube around, that now I will show you a photo, is already 400 grams. So in reality, we worked having a 600 grams of mass budget to develop what you see here. So here the concept is to have 4 chambers with 1 couple each of samples of materials that have to be actuated in space, so on the International Space Station, where we want on the samples, and I will show better, but that here you can see on the right, where we want to have the cold welding adhesion. So basically, each chamber hosts a spring-loaded mechanism where there is a plunger having one of the samples, and everything is actuated by a stepper motor controlled by a Raspberry Pi, plus there is a small camera to see that the actuation happened, plus there is a non-meter to measure the resistance of the samples. Now, here you see the team in Malta. We have to do the photo with the team here at MCAST. Here you can see the different stages of development of Astrobit. We worked with some mock-up with 3D printing parts. Here I didn't use a carbon fiber camera because they are very expensive spools, so it's a more traditional PLA. And this is a render done by SkyUp Academy. Also here we are collaborating with them because the level of mechanical rendering that they can do helped us also in providing the documentation to NASA. And here are a few pictures of the functional tests done in Houston, where basically Astrobit got qualified to fly on board a Falcon 9 rocket of SpaceX, and in October go on board the International Space Station. And in the group photo with the team of Nanoracks, you can see also Tiba near me. And it was really a challenging experience because when you start testing properly things, a lot of problems come out and you have a very little time to solve them. How was translated this? So this is the behind the scenes. So super cool, Houston, NASA, yes, amazing. The behind the scene was that the day in which I stayed less in the lab was 12 hours. So was really challenging, very little sleep. Luckily, we managed to get the experiment qualified. So the next steps are October, Falcon 9 rocket, go on board the International Space Station, and having the experiment installed on a module on board the International Space Station where it will stay 1 month. For our experiment, we don't need 1 month. Is just a few days, where we will actuate the chambers controlling the experiment from the ground station in Houston. So in Malta, we will have a mirroring of the interface they have, And being on the lovely Microsoft Teams, we will also interact with the engineers there to provide the correct commands and retrieve the data to analyze. Now, to close this presentation, I will explain a bit better why music from space. So, last February, we started also a collaboration with New York University, the branch in Abu Dhabi, that sponsored the project. So this helped us with the expenses. And there is Professor Andrea Macciò, that is the director of the Center of Astrophysics and Space Science, that saw this as a first step to collaborate further, and also they are interested in the results of the flight campaign. Now, besides this, with New York University, we also got interested in the part related to space music. What do I mean? In the sense that with 2 other missions, I already sent my music to the International Space Station. And the public outreach activity was from the International Space Station, there is an event where the music is streamed back to Earth. Now, this can look a bit strange, but from a point of view of outreach, is an excellent way to reach out to people outside your field of expertise. Now, space is not only for aerospace engineers. There is more and more medicine involved, space law, a lot of different professions. And it's a way to attract in a much easier way the interest of future students, but also the public opinion, because it's also the interest of the public opinion that is determining how much support the research activities have. Plus, I'm the only space pianist, at least till now, but the concept of space art is becoming bigger and bigger. There is International Astronautical Congress in October. It's the biggest event in aerospace. They are expecting 10,000 people this year. There is a full session in all the days dedicated to space art, where people from architecture, painting, and so on, presents different ideas that not necessarily went to space, but that are related to the space field. Now, for Astrobeat, I leveled up and I recorded new compositions at NYU in Abu Dhabi, also involving the students there, so students that has nothing to do with aerospace engineering, or in some cases even science. Plus, I started a collaboration with Tina Guo and Steve Mazzaro. Tina Guo is a Grammy-nominated, worldwide famous cellist, and Steve Mazzaro is a producer. Fun fact, they are both collaborating since many years with Hans Zimmer. Now, this collaboration is an excellent opportunity to amplify enormously the impact that a small project like Astrobeat, because physically also is very small, can have. Get the interest of people, and also getting the interest of bigger players in the field. So there are a lot of things, plus the fact that I'm a pianist, I love music, and I truly love to do something that goes to space and is streamed from space to Earth, and also is part of my evil plan not to conquer the world, because maximum I want to become the mayor of Australia. So I'm not interested to be the king of the world, but I want to go to space and play from there. That now can make you smile, but I will manage it. So this is all I have for today. Thank you for your attention, and if you have some questions, I'm happy to reply. Thank you.